Okay. Hello, everyone. Thanks for coming. So in this talk, I'll be presenting our paper, Mystique Uncovering Information Leakage from Browser Extensions. So, So browser extensions are small programs written in HTML, CSS, and JavaScript, and they run inside the browser. And their purpose is to give the users a programmatic way to configure their browsers. And in order for browser extensions to function, they need to have access to the visited pages, and also they have access to special privileged APIs. So this unique ability gives browser extensions access to the privacy-sensitive data of the users. And in this paper, we focus on understanding the privacy practices of third-party extensions that are publicly available for the Chrome and Opera browsers. So to give an example of the privacy implications of browser extensions, let's consider the example of the Web of Trust extension. So this is an extension that gives the users the reputation ratings for the websites that they visit. So here's a screenshot taken directly from the Chrome Web Store. And you can see here that this extension has a 4.5-star rating from more than 11,000 of its users, and it has more than 1.1 million total number of users. So the numbers seem to indicate that this extension is trustworthy. And if you then go to try to install it, it's going to ask you for permissions to access all the data on the website that you visit. So then you ask yourself, what if the extension authors then decide to abuse this data that they collect from you? So in 2016, this is exactly what happened. So here, journalists found out that the authors of the Web of Trust extension have been selling the data that they collect about their users to third-party agencies. So to summarize, the privacy implications of browser extensions come from the fact that, first of all, they have access to the visited pages. So what this means is they can inject arbitrary JavaScript code to be executed in the context of the visited pages. And the injected code will then have access to the DOM interface on that page. So one of the things they can do is that they can read the document location property, which would then give them access to the URL of the page. And they can also retrieve cookies from the website, and they can also read user inputs into form elements on that page, including usernames and password. Now, on top of this capability, extensions also have access to privileged extension APIs. So the extension APIs allow extensions to register callback handlers for events such as page load. And the callback handlers are usually provided with detailed information about the user's browsing activities. The extension APIs also allow extensions to query directly for browsing history information and to persist information to local storage to be retrieved later. And last but not least, being a program that runs inside a browser, browser extensions also have network access, so they can leak sensitive data that they collected over the network. So given the potential for privacy abuse, our goals in this paper are first to design and implement a system that can automatically detect whether privacy-sensitive information is being leaked by browser extensions. And then we want to apply such a system to large-scale analysis of browser extensions in regard to their privacy practices. So to introduce our system, we begin with a high-level overview. So on the left-hand side of the picture here, you can see a crawler that we use to periodically download the latest versions of all available extensions from online repositories, such as the Chrome Web Store. And then we store the downloaded extensions into a local database. Now, the rest of the picture shows the core of our system. So this system fetches the extensions from the local database, and it analyzes them one by loading them into a customized version of our Chrome browser, which is then automatically driven to visit the web. And then we log any network traffic or analysis output that's generated as a part of this process. So for our work, we modify the V8 JavaScript engine and the WebKit or Blink layout engine and the extension API, which I will expand on in this talk. So you can already see that our system implements dynamic analysis, and in particular, we implement dynamic taint tracking for JavaScript. which, as I mentioned, is the language that extensions are written in. So in such a system, we want to mark any information that's obtained from sensitive data sources as tainted. And as the extension code gets executed during runtime, we also want to make sure that any values that are derived from the sensitive data are also tainted. And finally, at the end of the analysis, we want to check to see if any taint sinks were triggered. For example, if there were any tainted data that was sent over the network. But implementing dynamic taint tracking for JavaScript is not without challenges. So the first reason is that the JavaScript language itself is quite complex. So as an example, an operation as simple as an addition operator can have different meanings depending on the operand types. And for a purpose of detecting privacy abuses by browser extensions, we need to be able to consider all available JavaScript data types. So we need to, for example, we need to consider string to number conversions and vice versa. Now, the complexities of the JavaScript language aside, the V8 JavaScript engine, which is the JavaScript JIT compiler used by the Chrome browser, is also quite complex. So the V8 engine has more than 1.3 million lines of code, and it compiles JavaScript to heavily optimized native code. So all of this basically means that we cannot rely on patching each individual data flow operations emitted by V8 to be taint aware. We need to do something smarter than that. And finally, there is also data flow paths that are not reflected at the JavaScript source level, such as those introduced by the DOM interface or the extension API. So to address the challenges, we will rely on the observation that V8, being a JavaScript JIT compiler, it has to have a copy of the JavaScript code that's ever going to be executed inside the Chrome browser. And one nice thing about the V8 engine is that it also keeps the source code available even after compilation, because it needs to support optimization and possibly de-optimization of the emitted native code. So our idea here is to basically implement dynamic taint tracking by supplementing it using information obtained from static analysis of the JavaScript source code. So to explain our approach, we'll be using this JavaScript function as our running example. So what this function does is that it reads the current page's URL by accessing the property location.href, which is considered as a taint source in our analysis. And then after that, it then performs a sequence of operations, which first makes an identical copy of the URL string inside the for loop from 9.7 to 9.14. And then it base 64 encodes the copied URL string. And then finally, it returns the encoded value on 9.17. So what's interesting about this function is how it makes the copy of the URL string, which is done inside the for loop. So what the for loop does is that it iterates through each character of the URL string, and then it compares it with a known value. And depending on the result of the comparison, it then decides which additional character to append to the copied string. So the purpose of the for loop here is to basically demonstrate why we need to consider control flow dependencies in our analysis, which I'll talk about in a bit. So given that the return value of this function is derived from values that are read from the property location.href, we need to somehow propagate taint from that to a return value. So how do we do that? We'll do that by modeling the data flows in the JavaScript source code by using static analysis to build a data flow graph, or DFG. And then we augment the DFG with control flow dependencies information. And finally, we also need to propagate taint across implicit data flows. So to build the data flow graph, we basically define edges in the DFG by defining them based on the assignment expressions in the JavaScript source code. And in this particular example, we have 4 assignment expressions that we consider when building the DFG. So these are circled in red here. Notice that we do not consider the assignment on 9.3 because that defines an object literal, and we do not want to over-taint properties in the object that really should not be tainted, such as the TS property here. So our analysis handles object literals by considering it in a separate case, which I'll talk about later. And also notice that we do not consider the assignment expressions on 9.6, 9.7, 9.10, and 9.12 because we know the right-hand side of those assignment expressions do not contain tainted values. So now if we go over each one of the 4 assignment expressions that we do consider, and we emit edges in the DFG for them. So we will emit 2 edges for the one on 9.2. Two more edges for the assignment on 9.4, 3 edges for the assignment on 9.8, and also finally 2 edges for the assignment on 9.16. So we have rules that we use to determine how edges are generated from the right-hand side if the right-hand side contains either a property access or a function call. But I will not go into the details of that. Please refer to our paper. So even after we have considered all the assignment expressions in the function, the graph is not quite connected because there's no path that goes from the taint source to the function's return value. So as I mentioned, we also need to consider control flow dependencies when building the DFG. And control flow dependencies in this example function are introduced by the for loop from 9.7 to 9.14, and also by the if statement that's contained within the for loop. So to encode control flow dependencies into the data flow graph, we basically treat the conditional expressions of control structures in the same way as the right-hand side of an expression. And we emit DFG edges going from that to the left-hand side of every assignment expression that's contained within the control structure. So here we see that we need to emit edges going from the variable I to variable C and output, and also from the variable length to C and length to output. So we encode that into the DFG. And then we do the same thing for the nested if statement. So we can see that we need an additional edge that goes from C to output. So we also put that into the DFG. But there's still one thing missing, which is the object literal definition on 9.3 that I mentioned before. So we consider this in a separate case known as implicit data flows. So implicit data flows are introduced whenever the value of an expression can be accessed at the JavaScript source level by any means other than explicit assignment. So the first example of this would be a function call. So during a function call, the expressions that define the values of the actual arguments are evaluated first, and then their resultant values are then given to the formal arguments of the function. And the second example would be an object literal definition, as we have seen before. So in such cases, the expressions that define the values of the object's properties are evaluated, and then their values are assigned to the object's properties. And this is also similarly the case for array literals. So to complete our example, we can see that there are 3 implicit data flows in this example function that's introduced by the object literal on 9.3. So the first one goes from the variable lock to the URL property. So we denote that in the DFG. And then we do the same things for the length property and also for the TS property. So now the graph is connected, and we can see there's a path going from the taint source to the function's return value. Now, I want to point out that in our current implementation, we do not encode the implicit data flows into the DFG, and then we handle taint propagation for them separately without using the DFG. So to propagate taint, we invoke our runtime taint propagation routine during at critical points during the execution of the JavaScript source code. So first of all, we need to propagate taint whenever we encounter function calls and function returns, because currently the static analysis that we use is intra-procedural when we are building the data flow graph. And we also need to propagate taint at the end of a basic block. This is necessary because some basic blocks can potentially be entered more than once, which is the case inside loop statements. And each time the basic block is entered, the code might operate on the tainted values differently. And finally, we also propagate taint whenever we encounter implicit data flows. So for the data flow paths that are now reflected at the JavaScript source level, so for those that are introduced by the DOM interface, we currently ensure that any tainted values written to the DOM will also be read back as tainted. And for the extension API, such as the message passing API and the local storage API, we modify their implementation so that they are taint aware. So we applied our system to analyzing more than 170,000 Chrome extensions and all of the Opera extensions that were available at the time of our analysis, which totals to about 2,800. So our analysis flagged about 3,800 Chrome extensions and 59 Opera extensions as potentially leaking privacy-sensitive data. So to estimate the true positive rates, so we just manually examined the tainted values that were detected as reaching taint sinks, and just to see if they contain privacy-sensitive data. So we did this for all of the 59 flagged Chrome extensions, and for our 3,800 flagged Chrome extensions, we verified against a random sample of 349 of them. And we were able to confirm that 77% of these extensions are true positives and about 8.8% of them to be false positives. Now, the two numbers don't add up to 100% because there are cases where we cannot say for sure whether they are true positives or false positives. In terms of the number of affected users, so here's a list of the top 10 flagged Chrome extensions that we verified should be true positives. And there are three things to notice in this slide. The first one is that the top 4 alone has a total number of more than 40 million users, and the top 10 has more than 60 million. So this shows the extent to which browser extensions can impact user privacy. The second thing to notice is that 7 out of the 10 extensions directly leak privacy-sensitive data over the network. And although the rest 3 of them only persisted such information to local storage, it is still possible that this information will be leaked later. And the last thing to notice is that 9 out of the 10 extensions here are security-related extensions. And the irony here is that the users go to install these extensions in order to improve their online security. But in reality, they get less security because their privacy is being abused. And now I want to talk about 2 case studies from our paper. So the first case study is the SimilarWeb Library. SimilarWeb is a company that makes an extension to provide users with the traffic ranking information on a website that they visit. But how does SimilarWeb obtain such data in the first place? Well, they do so by convincing other third-party extension developers to include their tracking library in their extension code. And from the results of our analysis, we found 382 extensions that included the SimilarWeb library code. And we also identified domains owned by SimilarWeb that received the leaked information. The second case study is the Web of Trust extension that I mentioned at the beginning of this talk. So the interesting thing about this extension is that it uses encryption before leaking data over the network. And if you are just observing the network traffic, you will not be able to detect the privacy abusing behavior of this extension. And although it can be argued that the functionalities of this extension requires it to query a remote server using the URL of the current web page, we, however, argue that this functionality can be implemented much less intrusively. For example, the extension can choose to only use the domain portion of the URL to query a remote server, or you can choose to distribute an offline reputations database. And as for the limitations of our approach, currently we do not cover all data flow paths that are introduced by the DOM interface or extension API. And of course, being a dynamic analysis system, we cannot detect behaviors that we do not trigger. And finally, we did not cover code coverage for the analyzed extensions in this paper. And we are open sourcing our Taint implementation for the Chromium browser. And we also plan to open source the script to replicate our experiments in the paper. And finally, we also provide a web interface to our system where users can upload extensions to be analyzed and get back the results. So please check the link. And in conclusion, we have proposed a dynamic analysis technique for JavaScript in the Chrome browser context. We applied it to large-scale analysis of Chrome and Opera extensions in regard to their privacy practices. And we identified privacy-abusing extensions that affect tens of millions of users. And with that, I would like to thank you.
All right, thank you very much for the talk. If you have any questions, please come up to the microphone and state your name and affiliation.
Andre Sabohold, Chalmers. One question that I had was about implicit flows. Part of your analysis was to build the tool to make sure that it actually tracks implicit flows. So what I was wondering is that how much of the extensions that you found were actually using implicit flows for leaks? Do you have any kind of idea how to estimate?
We don't have a number for that, but I would say there would be many of such implicit flows, because each time you call a function, you are introducing an implicit flow. And also, each time you define an object literal, you're also introducing implicit data flows. So I would say there will be plenty.
Okay. There's another question.
Have you seen any cases where what is being sent was maybe like a hash based on the URL, like a safe browsing API style query, or was it like always the somehow reversible?
So the majority of the cases are sent in plain text, but we do find cases such as the Web of Trust extension that uses RC4 encryption. And we also saw cases where they use the hash value of the URL. The hashed value of the URL.
We're getting close to me telling jokes, but okay. I do have a question still. The list of extensions, as you said, there's like the security extensions on top, right, of that list, with 10 million plus users. Do you have any idea for what those things, like for what those extensions might be using this information? So is there a particularly good reason? I think there's like some online safety, browser safety extensions where you could maybe argue maybe they have like their backend servers that need to check it's against a blacklist or something. Just whether you have any intuition on this.
Yeah, so for the Web of Trust extension, they do need to query a remote server to get back the information, but again, this is a gray area, right? So what if the company that makes these extensions then decide to abuse their users' privacy? So this is still something that we need to basically be aware of.
Mm-hmm. Okay. All right. If there's no further questions, then thanks again so much.